6 ohm resistor. This redraw leaves us with 3 resistors to combine. They're in series, so we just sum their resistances, which yields an equivalent resistance of 336 ohms. Which brings us to our final redraw. We've reduced our initial 6 resistors to a single equivalent resistance, which means we're done breaking it down. If we bend our circuit back together, reconnecting the positive and negative sides of the battery, it should be clear that we're left with our old ohmic friend, the simple circuit. And as far as the battery is concerned, that's all there ever was. No matter the circuit's configuration, the battery only sees an equivalent resistance and supplies the circuit with a corresponding current. How the circuit divvies up this current depends on the configuration. So we'll label the current leaving and re-entering the battery as I0. See, I told you we'd come back to drawing our currents. And now we'll determine a value for I0 using Ohm's law. We write V equals IR, which will solve for I, which in this situation gives us I0 equals the source voltage divided by the equivalent resistance. Inserting our values, we find that I0 equals 54 milliamps. Eureka! A value for current leaving and re-entering the battery marks the halfway point in our analysis, which means it's time to build it up now. To build our circuit back up to its original configuration, we'll move through our series of redraws in retrograde, determining the values for voltage across and current through each resistor as we go. So, we begin building it up by revisiting our 5th redraw. By the way, I'm redrawing my redraws here, hence the little 2, for the sake of neatness. But to save on time and paper at home, just simply mark up your old redraws. Okay, we know that I0 passes through the resistor, representing the equivalent resistance of these 3 resistors. And since there's only one path for the current, we know that I0 must pass through each of the 3 resistors. In other words, series resistors experience the same current, but provided the resistance values differ, they experience different voltages. Knowing the current through the resistors, we can now determine the voltage across them using Ohm's law. So for the 100 ohm resistor, we apply Ohm's law and we get the voltage across the 100 ohm resistor equals the current through the resistor, which is I0, that's 0.054 amperes, times the resistance of the resistor, which is of course 100 ohms. This yields a voltage drop across the resistor of 5.4 volts. Now for the 86 ohm resistor. V equals I, that's 0.054 amps, times R, 86 ohms, which equals 4.6 volts. And for the 150 ohm resistor, 0.054 amps times 150 ohms, which equals 8.1 volts. Now at this point, we could determine the power dissipation for the 2 outer resistors, but we'll just wait to calculate power until the end of the problem when we tabulate our solutions. Next, we revisit our 4th redraw, wherein junctions 1 and 3 are actual circuit junctions, where 3 or more paths come together. Here we have I0 splitting up into 2 currents at junction 1. What do we know about resistors in parallel? Well, we know they'll have the same voltage, but so long as they have differing resistances, they'll have different currents. And so we'll label the currents here I1 and I2. To determine values for I1 and I2, we'll use Ohm's law. But first we need voltages for these 2 resistors. We know that the voltage drop across the 86 ohm resistor is 4.6 volts. And since it represents parallel resistors, that means the voltage drop across each resistor is the same, 4.6 volts. And we'll box up this result to save for our solutions table. Solving Ohm's law for current, we determine that the current through the 120 ohm resistor, that is to say I1, equals 0.038 amps. Similar calculation for the 300 ohm resistor yields a value of 0.015 amps for I2. Now to our 3rd redraw. Here the 120 ohm resistor expands in a rather unexciting way. Out pops a goose egg resistor. I0 doesn't change. I1 passes through both the 120 ohm and 0 ohm resistor, and I2 is the same. We'll run the calculations for the sake of posterity with the unsurprising result that the voltage drop over the 0 ohm resistor is 0 volts. Onward and upward, or backward, depending on how you look at this method. In our 2nd redraw, we have an additional leg of this circuit, which means we need additional currents. Again, I0 and I2 don't change, but I1 is now divided between the 300 ohm and 200 ohm resistors here. So we'll call this one I3 and this one I4. To get values for I3 and I4, we'll use, you guessed it, Ohm's law. We need voltages first, but because they're in parallel, they have identical voltages to the resistor representing their equivalent resistance. That's 4.6 volts. We'll box that up for the 200 ohm resistor, and we determine current values using this voltage. So I3 is 0.015 amps, and I4 is 0.023 amps. Got the hang of this? Good. Now back to our first redraw. By the way, you'll likely be studying circuits with multiple power sources soon. And when you do, you'll need another circuit analysis tool, namely Kirchhoff's rules. Subscribe to my channel now, and when you need help with Kirchhoff's, come on back. Okay, I0 hasn't changed, so we'll draw that first. The current through this top leg containing the 50 ohm and 250 ohm resistors, that's I3 here. And the 200 ohm resistor is associated with I4. The current through the bottom leg, that's I2. And it looks like we forgot to label the current through the dummy resistor in our last redraw. That's just I1. So the final pieces of our circuit puzzle are the voltages across the 50 ohm and 250 ohm resistors. Again, it's just Ohm's law using the known current through the resistors. In this case, 0.015 amps, which yields a voltage of 0.75 volts for the 50 ohm resistor and 3.75 volts for the 250 ohm resistor. And with values for all of the currents and voltages, we're done building it back up. Now we'll generate a solutions table and calculate power dissipation for each resistor. With voltage and current in adjacent columns, power is a cinch to calculate. Recall that power dissipation for a resistor is equal to the product of the current and voltage. So we just multiply 0.75 volts and 0.015 amps, and we get 11 milliwatts for the 50 ohm resistor. For the 100 ohm resistor, we multiply 5.4 volts and 0.054 amps, and we get 0.292 watts. We'll fill in the table for the other resistors, collecting solutions from our redraws and determining power dissipation as we go. And that is how you break it down and build it up.